Let's take a look at thermodynamic processes. And when we look at thermodynamic processes, one of the most important tools we will use is the PV diagram, which is really just a pressure versus volume graph. And we're often going to look at ideal gases. So let's see, pressure, volume, ideal gases. That reminds me of Boyle's law. And let's remind ourselves of Boyle's law. Boyle's law tells us that the pressure is inversely proportional to the volume for a fixed mass at constant temperature. So let's say I'm in the PV diagram and I start out here at A. So my system is here at A, has a certain pressure, certain volume. And then let's say I change to a new state, B, and I do that by keeping the temperature constant. Well, if I do that, I'm going to move along this line. This line is a hyperbola. It's the graph of an inverse function, because remember, pressure is inversely proportional to the volume. Now, I can draw lots of different hyperbole, lots of different lines of inverse functions. And all of these lines show us how the pressure would vary with the volume at different values of a constant temperature. These lines are called isotherms, or sometimes isothermals. Iso means same, therm means temperature. Isotherms representing lower temperatures would be over here, and isotherms representing higher temperatures would be over here. These isotherms are going to be very useful in the future. All right. So we're going to consider changes to ideal gases. And in these changes, what we're often going to do is keep the mass fixed, but pretty much everything else can change. We can change the pressure, the volume, the temperature, the internal energy. We can do work on the system or have the system do work on the environment. We can transfer heat into the system or out of the system. There's a lot that can happen. Fortunately, in many realistic cases, something is going to stay fixed. So we're going to consider four kinds of thermodynamic processes, and in each one, something different is going to stay fixed. The first kind of process we're going to look at is isothermal. An isothermal process, you could probably guess, is one where the temperature remains constant. So here's our PV diagram, and we're going to imagine that we go from a state right here to a state right there by keeping the temperature constant. So we move along an isotherm. Now recall, for an ideal gas, the internal energy is equal to 3 halves nRT. So the change in the internal energy is equal to 3 halves times nR times the change in the temperature. But if we're talking about an isothermal process, then that means that the temperature is constant. The change in the temperature is zero. Well, if the change in the temperature is zero, that means the change in the internal energy is zero, according to that equation. So then the first law of thermodynamics, which is Q is equal to the change in U plus W, well, for an isothermal process, the change in the internal energy is zero. So for an isothermal process, Q is equal to W. Let's put that into words. In that case, the thermal energy that's added to the system is equal to the work done by the system on the environment. One way to interpret this is that if we transfer thermal energy to a system, well, that thermal energy isn't going into the internal energy of the system. It has to go somewhere, so it has to do work on the environment. The next kind of thermodynamic process we'll look at is isobaric. Isobaric means same pressure, constant pressure. Baric comes from the same root as, say, barometer, a pressure gauge. So let's get our PV diagram here. If it's isobaric, if it's constant pressure, then we'd move along a line like this between our states. So for this case, well, let's see, remember the work is equal to the area under the curve. If it's isobaric, if it's moving along like this, then the work is equal to the pressure times the change in the volume, because the area under that graph is just pressure times the change in the volume. So then let's look at the first law. Well, Q is equal to the change in U plus W. Well, W is P times delta V. So for an isobaric process, a constant pressure process, the thermal energy added, Q, is equal to the change in the internal energy plus P times delta V. And if we wanted to put that into words a little bit better, the thermal energy added, Q, can cause an increase in the internal energy, delta U, and it can do some work caused by the expansion of the gas, which is given by P delta V. And the next thermodynamic process we will look at is isovolumetric. It's a process where the volume remains constant. So if we have our PV diagram, if volume remains constant, then we're moving like this in the diagram. Now in this case, the change in the volume is zero. So let's see, the work done on the environment is equal to the pressure times the change in the volume. Well, if the change in the volume is zero, no work is done. So if we go to the first law, Q is equal to the change in the internal energy plus the work. But in an isovolumetric process, the work is zero. So in that case, Q is equal to delta U. The thermal energy that's transferred to the system is equal to the change in the internal energy of the system. All right. And the last type of process we'll look at is adiabatic. An adiabatic process is one where no thermal energy is transferred. So Q is equal to zero. Now on the PV diagram, it's a little bit tricky. So I'm going to draw in the isotherms. An adiabatic process looks a little bit like an isothermal process, but it doesn't follow an isotherm. It follows a different kind of curve. Now, Q is equal to zero in this case. So the first law, Q is equal to delta U plus W, is going to change this way. Q is equal to zero. So in that case, delta U is equal to negative W. So the change in the internal energy of the gas is equal to the negative of the work done by the gas on the environment. Now, without proof, I'm going to give you another relationship having to do with an adiabatic process. Turns out, for an adiabatic process with an ideal monatomic gas, we also have this relationship. P times V to the 5/3 is equal to a constant. Now, for just a moment, let me go back to that word monatomic. Monatomic means it's made of one atom. So it's not talking about diatomic hydrogen or diatomic nitrogen or carbon dioxide or water, nothing like that. It must be a individual atom. So say neon does this and helium. The noble gases will do this. Now, I'm not going to derive or really even explain where this relationship comes from, but it is true. Now, in chemistry, you might delve way more into this because in chemistry, there's this relationship that the pressure times the volume to some factor is equal to a constant, and that factor changes for different gases. And this factor is related to the specific heat capacity of the gases. But we're not going to go into that. I'll leave that to chemistry. So, back to thermodynamic processes. We can have a set of thermodynamic processes that we do one after another and that will make what's called a cycle, a thermodynamic cycle. So for example, let's imagine we have our PV diagram right here, and let's say our system starts right here in state 1. And then I move along an isotherm to a new state, state 2. And then I move at constant pressure over to state 3, and then I move at constant volume back to state 1. All right, now that I've returned to state 1, I could repeat the cycle again and again and again. So from 1 to 2, that's an isothermal process. From 2 to 3 here, that's isobaric. And from 3 to 1, that's isovolumetric. Turns out, if you do these cycles, well, it can be used to do work on the environment. So let's see why. The work done in the cycle from just 1 to 2 for that process, that isothermal process, well, the work done on the environment then is the area under the graph. And then the work done going from 2 to 3 in that isobaric process, well, there it's the negative of the area under the curve because I'm moving to the left in my graph. I'm decreasing my volume. And then the work done going from 3 to 1 in that isovolumetric, well, there's no work done in an isovolumetric process. So the total work done is the area under the curve from 1 to 2 minus the area under the curve from 2 to 3, which means we're left with this area. The total work that's done in that cycle is the area inside the cycle on the PV graph. And this leads us to the concept of a heat engine. A heat engine is a device which continuously converts thermal energy into useful work using a thermodynamic cycle. And I'm going to draw a couple examples of these thermodynamic cycles. Let's say I have a PV diagram here. Well, I could have an adiabatic change, and then an isothermal change, and then an isovolumetric change. And the work that's done in that process is the area inside the cycle. Or I could have something like this. Let's say it's isobaric, and then isothermal, and then isobaric in the opposite direction, and then isothermal back to start. Again, the work that's done on the environment is the area inside the cycle. Or I could have this. We could have isobaric, isovolumetric, isobaric in the opposite direction, and then isovolumetric in the opposite direction. Again, the total work done in that cycle is the area inside the cycle. And then I could have, let's see, isobaric, isovolumetric, and then adiabatic. And again, work done in the cycle on the environment is the area enclosed by the cycle. In each case, the work done is the area within the cycle as long as the upper curve goes to the right, as long as you're traveling along the upper curve to the right. Now, physically, what we would interpret that to mean is that the system must expand while it is hotter. And it might take a moment to figure that out, but take a look at these diagrams and see if you can understand why that is. All right, now we're going to define efficiency. So if you remember, we've seen efficiency before. Efficiency is the useful work divided by the input energy. It's that ratio. And many times when we talk about thermodynamic processes, we really want to know what the efficiency is of that thermodynamic process. But in every case of a thermodynamic cycle, somehow thermal energy is entering the system and then thermal energy is leaving the system. And the heat engine's job is it takes that energy, that thermal energy that's sort of passing through it. And as it passes through the heat engine, the job of the heat engine is to take some of it out and get some work done. So we often draw this diagram right here where there's a high temperature reservoir, so some kind of source of a high temperature, and there's a heat engine right here, and thermal energy passes from the high temperature reservoir into the heat engine, and then some thermal energy comes out and goes into a low temperature reservoir. But the job of the heat engine is it takes some of that thermal energy that's passing through and converts it into useful work that's done. So that's a sort of conceptual diagram that's often used to describe thermodynamic cycles. Now, there are many types of thermodynamic cycles. There's something called the Otto cycle, which is common in gas engines. There's something called the diesel cycle, which is common in diesel engines. But the most efficient possible thermodynamic cycle is called the Carnot cycle. And what distinguishes the Carnot cycle is it's a cycle that's completely made out of isothermal and adiabatic processes. So I'll show you what I mean. Here's a PV diagram. I'm going to draw in the isotherms. Let's say we start here. First, we're going to have an isothermal process. Moves along an isotherm. It's going to move to state 2. Then from 2 to 3, it's going to move in an adiabatic process. So it's going to move along a line we call an adiabat. And then from 3 to 4, it's going to be isothermal again. So move along an isotherm. And then from 4 to 1, adiabatic again. So it moves along this line we call an adiabat. And again, the work that's done by the Carnot cycle is the area enclosed by this curve. And it turns out that the efficiency of a Carnot cycle is equal to 1 minus Tc over Th, where Tc is the temperature of the cold reservoir and Th is the temperature of the hot reservoir, both in Kelvin. So you can see you'll get a greater efficiency if Tc is small and Th is large. In other words, you'll get a greater efficiency of a Carnot cycle if there's a greater temperature difference between the cold and hot reservoirs.